Okay, so in last meeting we talk about nuclear fission, fusion, and nuclear reactor. And let's try to solve detailed questions because in previous class we talk about the MCQs. Okay, so and we question number one from the past first and continue with the remaining question. Okay, so in question number two, emissions from a radioactive source pass through a hole in a LED screen and into a magnetic field as shown in figure 10.1. The experiment is carried out in a vacuum and we have multiple radioactive source. Sorry, we have a radioactive source placed on the left hand side. Okay, we have over here and there are basically three different observation or three different markings A, B, C on right hand side and the total distance is 3 centimeter, right? Okay. Next, we have some values of their count rates according to their radioactivity. And other question is from the data given for positions A, B, and C, deduce the type of emissions coming from the radioactive source. Explain your reasoning, right? Okay, so this is for basically B, C. Okay, now for you need to figure out that which type of we are going to receive at A, B, and C. So first, if we talk about A, so which type of radiation we are getting at point A? Or let's start from B because B is in the front of the radioactive source. So which type of radiation we are getting at B?
Gamma?
Gamma, because gamma rays will not deflect from magnetic field, right? Okay, so we are getting gamma over here. And what about A and C?
Could it be another ray from the electromagnetic spectrum?
Okay, but now we are having a radioactive source. So we need to identify in the sense of alpha, beta, and gamma, the radioactive radiations, right? If you remember, we talk about the properties of alpha, beta, and gamma. So alpha and beta both are going to be deflected from the magnetic field, right? So it means A and C both we have to just identify that which one is alpha and which one is gamma. Sorry, which one is beta. So you need to identify according to the properties of beta and gamma, which ray is going to. So one is going here at A and the other is downward over at B. So if you remember, according to the condition, according to the properties of alpha, beta, and gamma, alpha is greater in mass as compared to beta, and alpha is the heavy element or the heavy particle as compared to beta and gamma. So the deflection of alpha is less than the other particles, right? Or the other radiations. So at point A, we are receiving alpha, and at point C, we are receiving any confusion? Because beta is a fast moving electron and the mass of electron is less than the helium atom. So it will deflect with a greater angle, right?
Yes.
Okay. So we identify these radiations so that will help you to write the answer because we have to write with the reasons also. You to write with the and with reasons because we have multiple lines over here to write the answer. So if we start writing, so let's start with their identifications. For the given data for position ABC, deduce the type of emission. So first of all, we need to identify the type of emission. So at A, alpha radiation, right? we are getting
Gamma.
gamma, and at C we are getting. We have had the reason that identify these rays. So according to the property, first we start with the alpha. So alpha is greater to the of x less than beta, because mass beta is is less than alpha, right? Third, we have to identify the property of gamma. So radiation are neutral. So protection for and alpha can be affected by because it carry positive and negative charge, right? Okay.
Yes.
So I think in short, just to find out the all relevant point, and you may also write in detail by explaining each end point in, right? Okay, so question number 3, state the nature of gamma rays.
Neutral.
Yes,
Electromagnetic.
magnetic. Well, so these magnetic and charge or the neutral. Okay, so part B of this question, beam of alpha and beta particle passes in a vacuum between the poles of a strong magnet. Compare the deflection of the paths of two types of particles. So we already discussed in the last question that deflection of alpha particle is less than the deflection of beta particle, right?
Yes.
And one more important thing, because question is of 2 marks, so you need to identify another property. Deflection of alpha beta in opposite direction related to alpha and beta, that both will deflect in opposite direction. So different and direction is different, right? So continue with the other part. A beam of beta particle passes in a vacuum through the electric field between a pair of oppositely charged metal plates. Describe the path of the particles.
It will be deflected because it's affected by the electric field.
And in which direction it will deflect? Because we have electric field. Okay, I draw difference. So one plate is positively, which is positively, and beta is going to be passed between the plates. So in which direction it will deflect? Toward positive or negative?
It's negative, so it will go towards positive.
So towards positive because beta is already a negative, right? So it will deflect towards the positive charge because beta is negative charge. Okay, part D.
Oh, alpha.
State the nature of X alpha. Okay. Yes, because we are getting two number of proton and four number of nucleons. So nature of X is alpha. And calculate the value of A and Z.
202 and 84.
Okay, so we are getting 84 here, right? And 210. So for A, we are getting value, and for Z, we are getting value, right?
Yes, it's positively charged.
Yes, alpha particle is positive charge. Particle is positively charged, or we can say that it is equal to helium nu, right? Okay, next one.
Alpha particles will be attracted to the negative side and beta will be attracted to the positive side.
Yes. So we can identify with the reference of their deflection because beta will deflect towards positive and with greater deflection, right? So it means where we are getting greater deflection, so it means there is beta particle and that plate is positive. And where we are getting a small deflection, so that is alpha particle and that plate is negatively charged, right?
Yes,
And like the path of gamma rays in a magnetic field,
no deflection.
no deflection, it will move straight through the magnetic field because there is no charge on gamma rays. And state what is meant by the term isotopes. Use the term proton number and nucleon number in your explanation.
Atoms of the same element having the same number of protons but a different nucleon number.
Yes. So that is also the same concept, just like the chemistry. So you just need to answer or the right definition because both concepts in both subjects are same. The concept of isotope is not different. So that's why we start from radioactivity, and I told you that the previous chapter of nucleus is just related to the chemistry, just the isotopes, the atoms, all are the same. Okay, so number 5, an underground water pipe has cracked and water is leaking into the surrounding ground. Figure 11.1 shows a technician locating the position of the leak. Okay. A radioactive isotope is introduced into the water supply and the water that leaks from the crack is radioactive. The technician tries to locate an area above the pipe where the radioactive count rate is higher than in surrounding area. So main purpose or the main core of this whole explanation is that technician is finding the area or finding the radioactive count rate where the value of radioactive count rate is greater, because it means if the count rate is greater, so we are having a radioactive source over there, right? So that's why we are getting higher values. Okay.
Yes.
And the question is the statement that explain the type of radiation that must be emitted by the isotope for the leak to be detected. So you need to state and explain the type of radiation that must be emitted by the isotope for the leak to be detected. So there are multiple, so there are three types of radiation, and we know that alpha can be stopped by a paper, right? And beta can be stopped by few millimeters of aluminium. But if we talk about gamma, so for gamma, we need to have a lead or a concrete wall or safety over there to stop that radiation. So now which type of radiation we have to use over here?
Gamma.
Gamma, because gamma can easily penetrate through the ground. So that's why we are using gamma, highest penetration power, right? Gamma is going to be emit. So gamma emitter is used because the penetration power of is greater. Okay. Two, the half-life of the isotope used is 6 hours. Okay, so half-life is of 6 hours. Explain why an isotope with this half-life is suitable.
So that it's easily detectable.
Yes. Because we have enough time to detect the leakage. If we are using very low half-life of isotopes, so it means we are also getting less time to identify the cracks. So we need to again start the process again and again. So that is why starting in to detect the leak, right?
Yes.
And if we are using half-life of very short time, so it will disappear very quick. Okay, so now to fill this, and we have cesium over here. Is a stable isotope of element calcium, but calcium 135 is radioactive, or a nucleus of calcium 133 contains 78, and a nucleus of calcium 135 contains 80 neutrons. So 133 contains 78 and 35 contains 80 neutrons. Okay, pick one tick in each row of the table to indicate how the number of particles in a neutral atom of calcium 133 compares with the number of particles. So we need to compare between both isotopes. So one tick is over already there. So on the top side, particle in calcium 133, and on the lower side, we have multiple options with the comparison of calcium 135.
So proton and electrons are equal.
Okay, proton and electron, right?
Yes.
So 1 and 11 are equal. And for number of nucleons,
They have difference of 2.
yes, because initially we have number of neutrons of 2, so that's why the number of nucleons 2 fewer than calcium 135, right?
Yes.
Okay. Okay, so question number 6, the counter of a radiation detector placed close to a radioactive source gives a count rate of 1600 counts per second. Half-life is of 1 week. Ignoring background radiation, calculate the count rate 1 week after the first measurement.
800?
800, that is very simple. Half-life 1 week. So after 1 week, we are getting 800. Uh, okay. Part 2, 3 weeks after the first measurement.
200?
1600, 800, 400, 200, yes. So after 3 weeks, 4, right? Okay, now we have arrangement over here, position of samples, thick card, 5 mm steel, 20 centimeter lead, and the distance between the first card 20 cm. Sample containing 3 different radioactive sources are placed one at a time in the position shown. The table shows, okay, the table to indicate whether alpha, beta, gamma are emitted from each. So there are different positions and we need to identify according to this table. So if we talk about sample A, so sample A is high at A, B, C, D. Okay, so D is this one. So which particle?
Gamma?
Okay, so gamma can easily move from point A to T, and other particle can also do that because beta can easily penetrate through the. Okay, so the first one is gamma because it can be stopped because of D we have a 20 centimeter. So at D we are get gamma, and at C,
Beta?
yes, at C we are getting alpha, and at B getting alpha.
Alpha?
At D, A, B, and C is low. It means we have finally we have alpha. And state which type of radiation is most strongly ionizing. So which radiation has the highest ionizing power or ionization power? Alpha, beta, or gamma? So if you remember from the okay, we discussed about that alpha is greater in mass, so ionization power of alpha is greater among all these radiations, right? So alpha is the
Yes.
ionizing power. Okay, so these are some detailed questions. In next class, we will continue with the thermal section. Before that, you try to solve all the questions related to nuclear. I will send you the questions because we already almost done about the MCQs of this nuclear and we just need to solve the detailed questions. So this part will be completed shortly and quickly because this section is very much short and thermal will also be solved very quickly. So after that, we left out with only space physics, right?
Yes.